Transformers are amazing devices. They're the best example for electrical power transfer. If you can appreciate the way they do that, then you'll definitely agree that it's nothing short of magic. However, they're limited by their size and the cost when it comes to high power applications. So, when I want to create super high voltages on my workbench for experiments, the size and cost of power transformer is a big issue. Luckily, there is a way to overcome this and create high voltages using a special kind of transformer called the flyback transformer. So, without further ado, let's see what a flyback transformer is and how it is able to do what it does. If there's one magic component that makes generation of super high voltages possible, it is the flyback transformer. It is like the flux capacitor from Back to the Future that makes time travel possible, if you know what I mean. The flyback transformer is used in these old CRT monitors and television sets. Basically, you need such high voltages to create a magnetic field that is strong enough to deflect the electron beams inside the cathode ray tubes. By the way, the exact same principle is used to accelerate charged particles inside a particle accelerator, except that you get to smash atoms and blow stuff up. To understand how this is made possible, we need to understand its operating principle first. I have explained how a transformer works in a previous video, whose link should be on your screens now. Please watch it if you want to know more. Just like a power transformer, the flyback transformer also has a primary and secondary coil. But unlike the former, we can actually store energy in the flyback transformer in the form of magnetic field. The trick to all this is in the core of the transformer, which is made up of a material called ferrite, and it has an air gap. It seems so simple, but the difference it makes is so magical. Consider the magnetic flux as flowing water inside a pipe. The pipe contains the water inside it and never lets it fringe outside of its walls. Similarly, in a transformer, the magnetic flux produced are guided through the core material and it forms a magnetic circuit. Like an electric circuit, the magnetic circuit also is a closed loop, meaning the flux lines emerging from one end would have to reach the other end no matter what. Now comes the property called permeability. This is the property of a material which determines how contained the material keeps the magnetic flux within itself, just like the pipe which contains the water within its walls. Now, permeability varies from material to material. It is lower for iron but much higher for ferrite, meaning the ferrite core will keep the flux contained in it and provide a least resistance path for the flux lines. To be precise, resistance is not the word. The term to be used in a magnetic circuit is actually reluctance. It is the magnetic equivalent of electrical resistance. If a material has high reluctance, the less likely the flux lines are going to pass through it. It will pass, of course, but it prefers a least reluctance path. I mean, I know that I'll definitely choose an ice cream over carbonated drinks. You get my point, don't you? In a power transformer, the closed magnetic loop is formed by the laminated iron core. Since the permeability of that is less than ferrite, you need more of the material to keep the same amount of flux contained than a ferrite core would. Also, you can imagine the magnetic core in the power transformer to be analogous to a salt solution, the salt being the electric current and the salinity being the magnetic flux, with the core being the glass of water. As weird as it may sound, you'll see how it helps to understand what is actually happening in there. In the magnetic core of a transformer, the flux is directly proportional to the current flowing through the coil, meaning the salinity of the water depends on how much salt you can dissolve in the glass of water. If you continue adding the salt to the solution, its salinity keeps increasing, but there comes a point when any more salt added will no longer dissolve in the solution and it just stays there as a solid sediment at the bottom of the glass. This is called saturation. Similarly, after a certain point, the core of the transformer also gets saturated, and any increase in the current does not contribute to the additional magnetic flux through the core. So, any extra current only adds to the losses, and at this point, we say that the core is magnetically saturated. Now, you may ask, how does that explain the energy storage in a flyback transformer? The answer to that is the air gap. Look at this magnetic circuit. When you pass current through the winding, it creates a magnetic flux which is channelized by the ferrite core to complete the circuit, thus transferring the power from the primary to the secondary. Now consider that we introduce an air gap in the core. When you pass current through the winding, the same process gets repeated, but when the flux lines arrive at the air gap, it is faced with a medium of higher reluctance, in this case, the air in the gap. The flux now has to pass through it to get to the core, which is the least reluctance path to complete the circuit. Now, the flux lines start to fringe outwards, causing a non-uniform flux density in the core, before passing through the core again and completing the magnetic circuit. If you recall the water through the pipe analogy, you can understand that because of this, the core is no more saturated and you need extra current to maintain the flux density. This is exactly what enables storage of energy in the form of magnetic field in the air gap. Now, due to this, the leakage inductance increases and you would have to increase the number of turns to maintain the same amount of inductance value. This stored energy is what causes the flyback or the high voltage across the coils during changes in the input current. Now that we know how energy is stored in the air gap, let's see how we can use that stored energy for practical purposes. In my case, to create super high voltages. Consider this setup where the primary of the flyback transformer is excited by a DC supply. We can have the switching device like a BJT or MOSFET that is switched on or off by a clock signal whose on and off time can be controlled by us. So, we essentially have a time varying input current which is creating a corresponding magnetic flux in the ferrite core. This electrical energy is stored in the air gap in the form of magnetic field when the primary is excited, in other words, when the switch is closed. This is evident from the waveform where the primary current ramps up, storing energy in the magnetic field. Now, let's turn off the BJT or MOSFET for a moment. This is when we utilize the stored energy. Now, all of a sudden, the stored magnetic energy is released, which induces a current in the secondary, which then flows through the diode and eventually through the load, causing the current to ramp down. Now, two modes of operation are possible here. One, called the continuous conduction mode, where the BJT or MOSFET is turned on before the stored energy can be fully depleted into the secondary. And the second mode is discontinuous conduction, where the BJT or MOSFET is turned on after the stored energy is fully depleted into the secondary. In my case, I am concerned about producing high voltages, so I can just leave the secondary open circuited, thus stopping the current flow in the secondary. But the law of conservation of energy prohibits this because energy must be conserved. So it produces a super high voltage at the secondary which discharges through the stray capacitance to the ground, creating thousands of volts across the secondary. And just like that, we have super high voltages. Magic, isn't it? That brings us to the end of today's video. However, that's not all. I'm going to design a circuit to create a portable high voltage power supply for my high voltage experiments using the flyback method. So stay subscribed and wait for the next video. If you find the work interesting and if you were able to learn something new, then please consider subscribing to my channel and please press the bell icon so you won't miss any updates for the videos I upload. Share with your friends and hit that like button if you liked today's video. Until next time, engineer, experiment and educate. See ya.